This is Force's final review, presenting the answers for Physics CP. Directions. Following our horizontal and angled force problems, you'll need to draw a free body diagram for each. Number one, using the spring scale, you hang a metal block. The scale reads 22.5 newtons. What is the mass in kilograms of the block? So I just did this one on the previous video, but perhaps it's time to do it over again. So when I have a mass that is hanging from a spring scale, if I do a free body diagram, then the force of gravity acting down towards the center of the Earth is equal to the force of the spring scale, following Hooke's law, pulling up. And by the way, this K is not Boltzmann's constant. This is the spring constant K. They're both lowercase letter K. In problem number one, it states the spring scale's reading an upward force of 22.5 newtons. Therefore, since the mass is not accelerating, the weight of the hanging mass is also 22.5 newtons. And that is the product of mass times acceleration due to gravity. So if I take 22.5 and divide it by 9.80, I get 2.295918367, which becomes 2.30 kilograms. And that would be the answer to number one. Number two, you help your best friend move his 40-kilogram sofa. You attempt to push horizontally the sofa, but it does not move. The coefficient of static friction is 0.66 and kinetic friction is 0.24. You and your friend get the sofa moving at a constant velocity of 5.0 meters per second. Part A, calculate the minimum applied force to move the sofa. So if I use this rectangle to represent the sofa and do a free body diagram, of course, the weight of the sofa is its mass times gravity acceleration. This is a horizontal problem, so the normal force is going to be equal in magnitude to the weight of the sofa. By convention, the direction of motion is taken to be to the right unless stated otherwise. And let's see, we know that the mass is 40 kilograms. The coefficient of static friction is 0.66. And that's what we need to answer part A. The question is, what is the minimum applied force to move the sofa? The minimum applied force to the right has to just be equal to the force of static friction opposing its motion to the left. And we're not going to say, oh, plus 0.1 or something. No, we just set it mathematically equal to it and says, well, it's got to be at least this much. It's got to be greater than this much, perhaps. The force of friction is calculated using the coefficient of friction times the normal force. The normal force will be equal to the weight in this problem. So if I multiply the coefficient of static friction times the weight, I will have the maximum amount of static friction. The coefficient of friction was 0.66. The mass of the sofa was 40 kilograms. This takes place on planet Earth, where the acceleration due to gravity is 9.80 meters per second squared. And my calculator says I get 259 newtons as the maximum force of friction. And if that's the maximum force that friction can exert to stop this thing from moving, then my answer to part A is the minimum applied force has to be at least 259 newtons. Now, if I had rounded down to 259, I would still write it this way and say I need a minimum of 259 to the nearest newton. Part B, calculate the kinetic frictional force. Okay, well, the force of friction is equal to the coefficient of friction times the normal force. What's different in this situation is that we substitute the coefficient of kinetic friction for the coefficient of static friction. Static means it's not moving. Kinetic means now it is moving, and is quite typical. Kinetic friction is less than static friction. So now into my calculator, I type 0.24 times 40 times 9.80 meters per second squared. And by the way, this is the minimum applied force. The force of kinetic friction, I'm going to put it with a minus sign just to remind you that it's always opposing the direction of motion. And to 3 sig figs, it's 94.1 newtons. So that is my answer for part B. Part C, if you push the sofa with a constant acceleration of 0.65 meters per second squared, calculate the applied force. All right, so now for this one, you need to really think about what's going on. We have the force of gravity canceled by the normal force. We have the force of friction, which we now know of kinetic friction while it's sliding, is 94.1 newtons, opposing its motion. The applied force would have to be at least 94.1 newtons just to make this thing move at a constant velocity. But it has to also accelerate. So the applied force has to be greater than 94.1 newtons, such that when these two are added together, the net force is equal to the mass of the sofa times the acceleration of the sofa. In part C, the acceleration of the sofa is 0.65 meters per second squared. So the net force would be 40 kilograms times 0.65 meters per second squared, which means the net force is 26 newtons to the right. However, the question is, what is the applied force, not the net force? The applied force is 26 newtons to the right plus the additional 94.1 newtons it takes to overcome kinetic friction. So if I add 94.1 to 26, then my answer for part C, the applied force is 120 newtons to the right. Part E. No, part D. Oh, there is no part D. All right, well, problem 3. The following data was collected from the slider car activity, no friction while on the launcher arm. The mass of the slider car was given as 35 grams, length of the launcher arm 6.15 centimeters, distance traveled on the floor 290 centimeters, time on the floor 2.15 seconds. Part A, calculate the acceleration and initial velocity on the floor. I've already done this one as a video recording that has a duration of probably about 25 or so minutes, going in detail the history on this question. So right now I'm going to give a very brief recap and just say, look, go to the previous YouTube video that was posted and you'll see what's going on, or you'll get the history of it. So number 3, the story is, this is a 2-step, one-dimensional physics problem. In the first step, it starts from rest. So its initial velocity is 0. It accelerates at some constant acceleration over a distance of 6.5 centimeters, which I didn't write correctly, but there you go, 6.5 centimeters. And then it begins coasting, so not the scale, clearly, over a distance of 390 centimeters. Yep, which is, I'm just going to convert it immediately, 3.90 meters. And by the way, 6.5 centimeters is actually 0.065 meters when it comes around to it later on. It comes to rest again. And the time that it took for it to come to rest was 2.15 seconds. In part A, the question is calculate the acceleration and the initial velocity while it was on the floor. So this first physics problem is on the launcher arm. The second physics problem is on the floor. And the generic cross-sectional shape of these slider car toys is they looked like this originally. They're accelerated by a puff of air. You push down on it, poof, it launches it, and then it slides to a stop across the classroom, and you and your team carry out these measurements. Great. Now, to find the initial velocity on the floor, we note that we have 3 givens: final velocity, displacement, and time. and we want the initial velocity as it was moving across the floor. The equation that relates these four variables to each other is the one I refer to as the second kinematic equation of motion. Delta x is equal to 1/2, open parentheses, initial velocity plus final velocity, close parentheses, times time. Final velocity is 0. Rearranging and solving for initial velocity is going to be 2 delta x divided by t. Plugging in the numbers, 2 times 3.9 divided by 2.15, enter, has a value of 3.63 meters per second. So that actually answers part of part A. The second question is, what is the acceleration while it's on the floor? Well, I now have four givens: initial velocity, final velocity, displacement, and time. And the question is, so what is the acceleration on the floor? Well, to answer that, I can use equation 1, I can use equation 3, I can use equation 4. Pick whichever one that helps you get out the door with the right answer. I'm personally going to choose equation 1 because that's what I would think is simplest for me. And equation 1 says the final velocity is equal to the initial velocity plus the acceleration times time. The final velocity is 0. Rearranging for the acceleration, it's going to be the negative of the initial velocity divided by the time it took. And I'm just doing this at ludicrous speed. So on my calculator, I go 3.63 divided by 2.15, enter. I didn't re-enter the values, so here it is. I'm going to round off afterwards and say this is negative 1.69 meters per second squared. So these two values are the answer to part A. Part A, the question was, statement, calculate the acceleration and initial velocity on the floor. Answer, initial acceleration was negative 1.69 meters per second squared, which means slowed down by friction. Initial velocity was 3.63 meters per second as it flew off the launcher arm. Part B, calculate the frictional force between the car and the floor. Okay, well, if you were to do a free body diagram, you'd see the force of gravity acting down towards the center of the earth equal to the weight of the car, the normal force canceling that, and the force of friction stopping the car from sliding to the right. The friction force is the only force that isn't canceled. So that is the net force is equal to the mass of the car times its acceleration. The acceleration is negative 1.69 meters per second squared. The mass of the car was listed as 35 grams, which, knowing that there are 1,000 grams in a kilogram, and converting this to kilograms by moving the decimal point 3 places to the left, means I'm going to multiply 0.035 kilograms times negative 1.69 meters per second squared. And this will give me the net force. Again, I'm not going to bother clearing my calculator memory. I'm just going to use the previous result, and it says the net force is negative 0.0591 newtons. Now, if I'd cleared my calculator memory, this last digit might be a 2. I'm not going to punish you if you are as lazy as I am and don't round off until you are writing down your answer. For part B, it specifically asks, what is the frictional force between the car and the floor? So I've written the net force is this, but to just make it clear that I know what I'm doing, and this is part B, the frictional force is negative, meaning it's opposing to motion, really, 0.0591 or 2 newtons, depending on when you chose to round off the number in your calculator. Part C, calculate the coefficient of kinetic friction. Okay, so this question was covered in the previous video, and then students wanted me to reteach it. And so the previous video, if you keep playing it, you'll see it goes into that in even more detail. This is the one fun equation in all of physics, right? It's the only known equation in the entire universe. It's the only equation in the entire known universe that has a coefficient of friction in it. And it says, what it really says is the force of friction is the product of the coefficient of friction, the Greek letter mu, which became U in the American alphabet, English alphabet, times the normal force, which I wrote as N. See, fun is really force of friction is coefficient of friction times the normal force. Well, in this case, they're asking us to solve for the coefficient of kinetic friction. So you have to rearrange this equation and say the coefficient of kinetic friction is the magnitude of the force of friction divided by the magnitude of the normal force. The force of friction magnitude is 0.0591 newtons, and the normal force is the opposite of the weight, of course, and the weight is the product of its mass times acceleration due to gravity. So if I go 0.035 times 9.80, enter, it says the weight of that slider car is 0.343 newtons. So that goes in the denominator, 0.343 newtons. The units cancel. You can never have a negative coefficient of friction. Zero coefficient would mean that it's frictionless. And if I type 0.0591 divided by 0.343, enter, it says beep, 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 the coefficient of kinetic friction is 0.172 to 3 sig figs. And I'm hoping you kind of override the text and actually calculate things to 3 sig figs. So formally, part C, the answer is the coefficient of kinetic friction, sliding friction, has a value of 0.172. And no, it's not negative, even though friction is. Part D, calculate the applied force on the launcher arm. Okay, so the understanding you have to have is that the initial velocity while it slid across the floor is the final velocity as it accelerated on the launcher arm. And now we have three givens: initial velocity, final velocity, displacement, and we need to calculate what is the acceleration as our one unknown. We cannot use the time that it was on the floor. The time it spent accelerating is actually a tiny fraction of 1 second, faster than you can measure by normal means. Instead, I would pull out the force kinematic equation of motion, which says the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. Initial velocity is 0. So rearranging for the acceleration on the launcher arm, we have final velocity squared divided by 2 times divided by the length of the launcher arm. The numbers you would plug in are 3.63 meters per second in the numerator, quantity squared, divided by 2, divided by the length of the launcher arm in meters of 0.065 meters. 3.63 squared divided by 2 divided by 0.065, enter, is 101 meters per second squared. But part D didn't ask for the acceleration, it asked for the applied force. And we're presuming that there's no friction on the launcher arm because that's what I told you to assume. We can't actually solve it if there is friction. We don't have a good way of determining how much there is. So the net force on the launcher arm is the applied force because there's no friction, is the mass of the slider car times the acceleration on the launcher arm. And when you multiply 101 meters per second squared by 0.035 kilograms, you get 3.55 newtons. Number 4. A wooden block is pulled at an angle of 31 degrees above the horizontal with a force of 35 newtons. The wooden block accelerates at a constant rate of 0.454 meters per second squared. The kinetic frictional force is 10 newtons, sadly written to only 1 sig fig. And part A, calculate the horizontal and vertical applied forces. Okay, so now that you've carefully read the problem, of course you're going to do a sketch of this problem. And I have a wooden block. I'm applying a force at an angle of 31 degrees above the horizontal, and it says this horizontal with the applied force is 35 newtons, and The wood block has an acceleration of 0.454 meters per second squared, and that there's kinetic friction of 10 newtons. Great. Part A, calculate the horizontal and vertical applied forces. Okay, so for that one, look, here's a sketch of just the applied force. It has a horizontal component, the Fax. It has a vertical component, the Phi, where Fax means the X component, the applied force. Phi means the Y component, the applied force. They're perpendicular to each other. This forms a right triangle. The angle theta here is 31 degrees. The hypotenuse is listed as 35 newtons. That's 31 degrees, 35 newtons. And I use SOHCAHTOA to answer part A. They're asking calculate the horizontal and vertical applied forces. The horizontal component is the adjacent side of this right triangle. The hypotenuse is given 35 newtons, the angle is given, so I'm going to choose cosine of 31 degrees is equal to the adjacent side, the Fax, divided by the hypotenuse of 35 newtons. To solve for the adjacent side, I multiply both sides by 35 newtons. First, make sure that your calculator is set to degrees, not radians. So if I type in 35 cosine 31, it says the answer is pretty much exactly 30.0 newtons as far as we're concerned. So the x component of the applied force is 30.0 newtons. To get the y component, I know it is the opposite side of this right triangle. And I'm going to use the relationship that the sine of 31 degrees is the Phi divided by 35 newtons. Again, multiplying both sides by 35 newtons, I have 35 sine 31, enter, and then I get 18.0 newtons. So the Phi is 18.0 newtons. This ends part A. Part B, calculate the mass of the wooden block. Interesting, right? Interesting. So that's an unknown right now. But what we can say is, look, vertically it doesn't leave the ground. So I'm only interested in what's going on horizontally. If I draw the horizontal force, I see I have an applied force horizontally of 30 newtons. That's the Fax. I have a frictional force of 10 newtons. That's given. When I combine these two forces, I have a net force, which is equal to the unknown mass of this block times its acceleration. But its acceleration is known, and the net force is now knowable. So what we have, if 30 newtons to the right, 10 newtons to the left, means the net force is 20 newtons. The mass is unknown, but the acceleration is given as 0.454 meters per second squared. Dividing both sides by the acceleration. For part B, the mass is 20 divided by 0.454, enter. I get 44.0528634, which means I'm going to write down 44.1 kilograms. Pretty big block compared to what I normally have you students do. Part C, calculate the normal force. All right, so to answer that one, of course, we can now calculate the force of gravity, which is equal to the weight of the object. And in previous problems, there were no vertical forces other than the normal force. So the normal force was equal to the weight. But in this problem, there is an upward component to the applied force in an amount of 18 newtons. So the Phi is pushing upward with a force of 18 newtons. The wooden block, as near as we can tell, never leaves the surface of the table. Therefore, the sum of all the forces in a vertical direction have to add up to zero. Therefore, the normal force added to the y component of the applied force has to be equal to the weight of the object. And in this question, they're asking, please calculate the normal force. Well, first, now that I know the mass of this block, I'm going to calculate its weight. So if I go 44.1 times 9.80, enter, it says the weight is 432 newtons. That's the magnitude of the downward force. If I remove 18 newtons from that result, then the upward normal force, this is part C, the upward normal force is just 414 newtons. It is less than the weight by 18 newtons. Part D, calculate the coefficient of kinetic friction. This does not depend on the speed. It only depends on the Fun equation. Fun, the force of kinetic friction is equal to the product of the coefficient of kinetic friction times the normal force. Note that you had to calculate the normal force correctly in part C in order to use it in part D. So in part D, you're to calculate the coefficient of kinetic friction. That means rearranging this equation, taking the magnitude of the force of friction and dividing it by the magnitude of the normal force. The magnitude of the force of kinetic friction was 10 newtons. The magnitude of the normal force was 414 newtons. Therefore, in this problem, after you go 10 divided by 414, enter, you see that the coefficient of kinetic friction is a value of 0.02. Now, I have students who stop there and they say, oh, here's my answer. Yeah, but you've only given it to one significant figure. The zeros are just placeholders to the left. So I want to see it to 3 sig figs. So give me some more digits. Now it's to 2 sig figs. And I'm going to round up this 15 to a 2 and say, here's the answer to 3 significant figures. Problem 5. You push your shopping cart, mass 20 kilograms, with an applied force 40.0 degrees below the horizontal of magnitude 25 newtons. The coefficient of kinetic friction is 0.32. Calculate all this stuff. All right, well, I'm not going to bother drawing the shopping cart in a very meaningful way. I'm just going to draw a box and say, look, there's the force of gravity acting down equal to its weight. There is the applied force going down and to the right. And that applied force has a magnitude of, great, 25 newtons at 40 degrees below the horizontal. The coefficient of kinetic, and there's the normal force, which by the way is going to be greater than the weight this time, and there's friction. Okay, well, so they are telling us that the coefficient of kinetic friction has a value of 0.32. And in part A, the question is calculate the horizontal and vertical applied forces. So once again, I'm going to build a right triangle. The angle is 40 degrees below the horizontal. The hypotenuse is 25 newtons. I need the facts and I need the phi. Definitely I need phi. So, right triangle. Again, cosine is the adjacent side, sine is the opposite side. So the x component of the applied force is going to be 25 cosine 40 degrees. Enter. Calculator says 19.2 newtons. Phi is 25 sine 40, 16.1 newtons. And by the way, that is downward. The x component is to the right, and the y component is downward. So there is the answer to part A. Part B, to calculate the normal force, look at your free body diagram. You have the force of gravity going down. You have the y component of the applied force going down, and the shopping cart doesn't actually go into the earth. So the normal force must be equal to the sum of the weight of the shopping cart plus the y component of the shopping cart. Its mass is 20 kilograms. So that makes the weight, you can do this one in your head, I know, but 20 times 9.8 is 196 newtons downward. The y component of the applied force is 16.1 newtons downward. So when you add those two together, you have a normal force that cancels it of 212 newtons. And that's the answer to part B. Part C, calculate the kinetic frictional force. All right, well, again, looking at the free body diagram in this case, there's the facts. The x component of the applied force to the right, there's friction opposing it to the left, combined, because I'm canceling the vertical forces. Combined, I have the net force acting to the right, which is the product of the mass of the shopping cart times its acceleration to the right. Now, the mass of the shopping cart is given as 20 kilograms. The acceleration of the shopping cart to the right, I'm sorry, I'm doing part D. I should really be doing part C. Part C, calculate the kinetic frictional force. Well, let me think about that. I'm saying I don't know the kinetic frictional force. Oh, I'm sorry, it's given. The coefficient of kinetic friction is 0.32. So the equation is the fun one. The force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. That's why the previous part was calculate the normal force. The value of the coefficient of kinetic friction is 0.32. So I'm going to go 212 times 0.32, enter, is 67.8 newtons. There we go. The force of kinetic friction is 67.8 newtons, and it's opposing its motion, so I'm going to stick a minus sign in front of it just to make it kind of obvious that that is my answer to part C. Now I can do party. Yes, it's party time, or part D. Horizontally, the applied force is the facts, which was 19.2 newtons. The force of kinetic friction is way larger. It's 67.8 newtons. So this thing is going to be slowing down. And to calculate the horizontal acceleration, we first need to calculate the net force, which is going to be the difference between friction of 67.8 newtons and the applied force in the horizontal direction of 19.2 newtons. the net force is trying to stop it 48.6 newtons, and that's equal to the mass of the shopping cart times its acceleration. For part D, they want you to calculate the acceleration. So take that value, divide it by the mass of the cart, and I have an acceleration of negative 2.43 meters per second squared. Part E, calculate the horizontal acceleration if you let go of the shopping cart. Well, for that one, now I don't even have 19.2 newtons trying to prevent it from stopping. All of the force of kinetic friction, 67.8 newtons, is applied in stopping the shopping cart. So now the acceleration is going to increase to negative 3.39 meters per second squared, and that is the answer to part E. For the next three problems, 6, 7, and 8, it's using material that we did not cover this school year, but for completeness, wouldn't it be nice to have the answers? All right, so for number 6, part A, calculate the gravitational force between the sun and Mars. And the equation is the force of gravitational of attraction is the product of the universal gravitational constant times mass 1 times mass 2 divided by the distance between the two masses, center to center, squared. And G, the universal gravitational constant, has a value of 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. Great. So in problem 6, part A, you're going to be plugging in G times the mass of the sun, which is 1.99 times 10 to the 30th power kilograms, times the mass of Mars, which is 6.42 times 10 to the 23rd power kilograms, and you're going to divide that by the distance from the center of the sun to the center of Mars squared. And the distance from the center of the sun to the center of Mars on average is 2.28 times 10 to the 11th power meters. You're going to square that number. All right, so the force of gravitational attraction would work out to be, I'm curious. Oh, yeah. So I have G already stored in my calculator memory, so that makes it convenient for these problems. I'm going to go alpha G times 1.99 times 10 to the 30th power times 6.42 times 10 to the 23rd power divided by 2.28 times 10 to the 11th power x squared, button, enter. And my calculator says, I'm going to put a minus sign just because it's an attractive force. And we use minus signs in electricity to show that it's attractive. We also do that in gravitation. Negative 1.64 times 10 to the 21st power newtons. You might recall that a mole is 6.022 times 10 to the 23rd power. So this is getting into the realm of like 1% of a mole of newtons. You should think of that and say, that's a lot. Okay, so part A, there's my answer. For part B, it says now do the same thing for the planet Mercury instead of the planet Mars. And so you cross out the mass for Mercury, you cross out the distance from, you cross out the mass for Mars, replace it with the mass of Mercury. Cross out the distance from the Sun to Mars, and replace it with the distance from Sun to Mercury. Well, like the table says, it's going to be alpha G times 1.99 times 10 to the 30th power for the Sun times 3.3 times 10 to the 23rd power for Mercury divided by 5.79 times 10 to the 10th power x squared, enter. Beep, beep, beep. There is the result. And what that says is the force of gravity is attractive, and the value is 1.31 times 10 to the 22nd power newtons. So now this is, nearly 10 times greater, and it's starting to approach Avogadro's number of newtons, right? 6.02 times 10 to the 23rd power. So this is, it's above 1% of that. Anyways, it's starting to get up there. There's my answer to problem 6, part B. And that's the end of that printout. But wait, there's the second page. Sorry that it took 2 pages. Problem 7. The space shuttle, 15,000 kilograms, is located 2 times 10 to the 5th meters above the surface of the Earth. Calculate the gravitational force between the shuttle and the Earth. For number 7, you have to maybe do a sketch that shows, not to scale, here's the Earth, and then at a distance h above the Earth is where the space shuttle is in orbit. So the true distance from the center of the Earth to the space shuttle, r, is equal to the radius of the Earth plus the altitude of the space shuttle above the surface of the Earth. So those are the numbers that you're going to be plugging in to Newton's law of universal gravitation. It's going to be attractive g times the mass of the space shuttle, which is 15,000 kilograms, times the mass of the Earth, 5.974, but in this handout it's 5.98 times 10 to the 24th power kilograms, nearly 10 moles of kilograms, in other words, divided by, and here you need to be careful that it's all in the same units, the radius of the Earth is 6,378.14 kilometers, listed here as 6.38 times 10 to the 6th power meters. And we're going to add to that the altitude of the space shuttle as 2 times 10 to the 5th power meters. So plus 2 times 10 to the 5th power meters, close parentheses, quantity squared. Now, if you're good with scientific notation, you'll recognize that 2 times 10 to the 5th is 0.2 times 10 to the 6th. And so really this works out to 6.58 times 10 to the 6th power. You just type it in that way. Otherwise, you go alpha g, 15,000 times 5.98 times 10 to the 24th divided by, and you can actually do this by open parentheses, 6.38 times 10 to the 6th plus 2 times 10 to the 5th, close parentheses, x squared, enter. And it says you get 138 kilonewtons. So, of course, attractive, negative 138 kilonewtons. This is down in the realm where, yeah, you could be using the Greek prefixes. Kilo, of course, means thousands. So 138,000 newtons. Number 8, calculate the acceleration due to gravity on Venus. This one is already done on the previous video, but here it is again. If the average mass of an adult is 65 kilograms, what is the weight of an average adult on Venus? Well, so let's go to Venus. When you're on Venus, there you are, standing on Venus. The force of gravitational attraction between you and Venus is universal gravitational constant, of course it's attractive, times the mass of you, times the mass of Venus, divided by the distance from the center of you to the center of Venus squared. Now, the space shuttle was 200,000 meters above the surface of the Earth. That made it barely significant, right? 6.58 instead of 6.38. You are 2 meters above the surface of the Earth, and really 1 meter to your center of mass at best. So adding 1 meter to the radius of the Earth is insignificant for this problem. So the distance from the center of the Earth to the center of you, for all practical purposes, is the radius of the Earth. And this force of gravitational attraction between you and the Earth is also known as your weight. So wait a minute. If this is the same thing as your weight, then this little m is your mass, this little m is your mass. If we cancel them out, you have the discovery that the gravitational attraction on the surface of any planet is the product of the universal gravitational constant times the mass of that planet divided by the radius of that planet squared. We can apply that here to calculate the acceleration due to gravity on the surface of Venus. The acceleration due to gravity is going to be g. Looking it up, the mass of Venus is listed as 4.87 times 10 to the 24th power kilograms. The radius of Venus is listed as 6.05 times 10 to the 6th power meters. And of course, you're going to square that quantity before you press the enter key, hopefully, and go alpha g times 4.87 times 10 to the 24th divided by 6.05 times 10 to the 6th x squared, enter. The acceleration due to gravity on the surface of Venus is 8.88 meters per second squared, of course, in the downward direction. And that is one of the questions in number 8. They ask, calculate the acceleration due to gravity on Venus. And so my answer is the acceleration due to gravity on a planet Venus is 8.88 meters per second squared down towards the center of the planet. Now, the follow-up question is, so you, adult, have a mass of 65 kilograms. How much do you weigh on Venus? And the answer is, well, okay, that would be equal to my mass times the acceleration due to gravity on Venus. By the way, if you didn't get part A, you could still solve this by just plugging the numbers into Newton's law of universal gravitation. But I'm going to take my answer, I'm going to round it. So 65 times 8.88, enter, and my calculator says the answer is 577 newtons is how much you weigh on Venus. This concludes providing you with the answers to course's final review.